In this problem, we're given three forces as shown in the diagram and asked to determine the magnitude and coordinate direction angles of the resultant force. So we will solve this problem in three steps. The first step being to express each force in Cartesian form. The second step being to add those forces that are now in Cartesian form together to find the resultant force in Cartesian form. And then the third step is to calculate the magnitude and direction of the resultant force from the Cartesian form of the resultant force. So let's start with step one. And we'll look at F sub 1 first. F sub 1 is a 90-pound force that doesn't have any given direction angles associated with it, but we do notice that it acts through point A, and it also acts through the origin, which remember is just 0, 0, 0. So F1 is the case of a force vector directed along a line or a known line. So we can write F1 as its magnitude, we'll just call that F1 non-vector, times a unit vector along the direction of the line in the same along the line in the same direction as F sub 1. And that will be, we'll call that the unit vector sub OA. Now we know that F1 is 90 pounds, and a unit vector along the line OA in the direction of F1 can be expressed as a position vector from O to A divided by the magnitude of that position vector. Okay, now let's look at the position vector R from O to A first. The position vector R sub OA can be calculated by taking the x-coordinate of A, 4, subtracting the x-coordinate of the origin, 0, I, plus the y-coordinate of A minus the y-coordinate of the origin. So there's going to be no y term or j term in this position vector, plus the z-coordinate of A minus the z-coordinate of the origin. Okay. So we'll simplify that, and we'll get that that position vector is 4i plus 3k. No j term. Now the magnitude of R sub OA is going to be the square root of the squares of these three calculations, which is going to give us 4 squared plus 0 squared plus 3 squared. And if we do that math, we get 5. So now we can write U sub OA as R sub OA for I plus 3K over the magnitude of R sub OA okay, and we said that the vector f sub 1 equals f sub 1, the magnitude of f sub 1, times that unit vector. Okay, and we do some more math there, and we end up with the vector f sub 1 written in Cartesian form as 72i plus 54k. Okay. Now we'll look at f sub 2. Now notice with f sub 2, we're given a couple angles with respect to, one angle with respect to the xy plane and another angle with respect to a line in the xy plane. So let's see what we can do with those. And for now, I'm going to say, just draw a circle around this because this is one of our intermediate results. And now for f sub 2, move over here, I'm going to use those angles in some trigonometry, and I'm going to say that the I component of f sub 2 can be written as the magnitude of f sub 2, which is 150, times the cosine of 60. Now here's f sub 2 here. Okay. And I'm going to get the I component of f sub 2, which I'm going to show as out here for convenience with the trig. We know it acts through the origin, but I can show it out here and understand that it acts through the origin just for convenience. So this component here, the x component of f sub 2, is going to be 150 times the cosine of 60, which is going to get me this distance here. And then if I take that distance and multiply it by the sine of 45, that will get me this distance here. Now let's look at that. Remember that this is a right angle here. So I'm taking the magnitude of f sub 2, multiplying it by the cosine of 60. That's getting me the magnitude of this line here, and then remember that this triangle in the XY plane is a right triangle, and I'm looking for the side opposite the 45-degree angle. This is the hypotenuse, so I can multiply my previous result by 45 degrees, and that will get me this magnitude. Okay. This is going to be the J term. The J term is going to be similar. I want that intermediate hypotenuse that's in the XY plane. So I'm going to say 150 times cos 60. I meant to write that in black. And now I'm looking for this side. So it's going to be times the cosine of 45 degrees, J. And the K term is actually the easiest, where the K term is going to be this distance here. And remember, that's in a right triangle, so it's going to be the 150 times the sine of 60 degrees K. Okay. So now I have f sub 2. Well, I don't have it yet. I need to simplify that. I'm going to do that math, and I'm going to end up with 53.03i plus 53.03j plus 129.9k. Remember, we need to store all of those calculations in our calculator. I've rounded for the sake of the handwritten portion of this, but you need to keep those numbers in your calculator. We're not going to round the overall calculation until the very end. So we have f sub 2, and now we need to find f sub 3, which is actually the easiest of these three forces to put into Cartesian form. By inspection, that we can see that f sub 3 has a magnitude of 200 pounds, and it acts along the z-axis, or in the positive k direction. So there's f sub 3, and that is step 1, and that's usually the most tedious part of these type problems, getting all the vectors into Cartesian form, and you need to stay vigilant and watch the minus signs if you have any. We didn't have any in this problem, but you need to be careful, check for mistakes, because any mistakes you make here are going to be carried on through the second and third steps. Okay, so I now need to get myself some more space here. I think we can deal with this much here. Okay, so now step 2. Put step 2 here just to save some space. Step 2, now that we have all the vectors in Cartesian form, we're going to add them together In other words, the force resultant is equal to the sum of the three forces. And we are going to do that by adding together first the I terms, which is going to be 72I, and we can do these in colors here. We're going to add the 72I to the 53.03I to F3 has no I term. So, yeah, let's do it like this. So we have 72 plus 53.03 I plus our J terms. Use purple for J. No J terms in F sub 1. A J term in F sub 2 of 53.03. And no J terms in F sub 3. And last, we'll write our K terms in blue. We have 54K plus 129.9 plus 200, and that's all K. So we do that math, and we end up with F sub r, not F sub 2, equals 125.03 I plus 53.03 J plus 383.9 K. That is step 2, and its result is having F sub r, the resultant force, in Cartesian form. So if the problem asks us to find F sub r in Cartesian form, we would stop here, and this would be our answer. But it wants to know, we're asked for the magnitude of F sub r, as well as the coordinate direction angles of F sub r. So we will go on to step 3. The magnitude of F sub r is given by the square root of the sum of the squares of the I, J, and K components. And again, these are those numbers rounded, but I've kept these in my calculator and will not do any actual rounding until the final answer. Now I do this math and I find that F sub r equals 407.22 newtons, and this is the final answer for the magnitude, so I can round that to 3 significant figures, and the magnitude is 407 newtons. The magnitude of the resultant force is 407 newtons. Now I've still kept that 407.22 and all the rest of its decimal places in my calculator. I'm going to use that for the coordinate direction angles. And my first coordinate direction angle alpha, I'm going to calculate by taking the inverse cosine of the x component of my Cartesian vector. And we can do that again in, well, that's okay, we can do it in orange. So that'll be 125.03 over the magnitude of f sub r, which is 407.22. And I do that math and get 72.1 degrees. Beta is going to be the inverse cosine of the y or j component of the Cartesian form of my force resultant, which is 53.03. divided by 407.22. That'll give me 82.5 degrees. And finally, gamma is the inverse cosine of my z or k component of the force resulted in Cartesian form, 383.9 over 407.22, and that math comes out to 19.5 degrees. So here are the coordinate direction angles of the force resultant, and here is the magnitude of the force resultant, and that's what the problem asks for.